So I'm going to take a little bit of time right now and talk about some information that's in Appendix E of the book. This is talking about sigma notation, which comes in the next couple sections. And so if you don't remember it from pre-calculus, I'm just going to kind of give you a crash course on it, but you may want to check out Appendix E if you need more than that. So sigma notation is the idea of summation notation using the Greek value sigma, which is what you see multiple times on this slide. So notice it says recall, because this is talked about in pre-calculus courses, the college algebra and pre-calculus. So it's used when we want to, for example, in A, we want to write 1 plus 2 plus 3 plus blah, 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 all the way up to 100, but in a succinct way without having to write it out like we see. So we use sigma, which indicates that we're going to be summing something, adding things together. We often use the letter I to denote where we're starting. So I'm going to start with 1, that I is going to be 1. And in this case, I have 100 terms. So up at the top goes where I stop. So that's going to be 100. Then what I'm adding up is just 1 plus 2 plus 3. And that's what happens as I changes. So what I have inside is just I. So when I is 1, I get 1. And then the summation notation tells me to then add what happens when I is 2 plus what happens when I is 3. And so in this case, that's just 1 plus 2 plus 3 plus 4, again, all the way up to 100. So the next one that we see for B is the opposite. This is now saying interpret what you see here for B. So in this case, we start with I being 1 and we go out up to I being 5. So when I is 1, we have 1 squared. And when I is 2, we have 2 squared. And when I is 3, we have 3 squared. And when I is 4, excuse me, we have 4 squared. And when I is 5, we have 5 squared. And of course, these can be added together if you want. The point is more just to see that that notation is telling us place the values from 1 to 5 in for I, and every time you do a placement, put an addition sign and then add the next term. So those are just 2 general ideas. What we're going to be using in this class, the properties that we're going to use, is the fact that from I equaling 1 to n of just 1 is n. And that's because this is really just 1 plus 1 plus 1 plus 1 plus 1 plus 1 n times, because there's no I in it. So nothing changes. It's just adding the same value over and over. Now for number 2, C is just a constant, but notice C is not I. So you could arguably see this as C times, and then I equals 1 up to n of 1, and we already found that that was n, so C times n. Now, the next one for I is similar to basically both of them that we've seen. However, this one follows, number 3 here, follows a very specific pattern, and this would be something you could prove using induction if you've ever, if you did that in your pre-calculus class. But there is actually a formula for this, and it's n times n plus 1 over 2. So it means if you know, and this is a party trick you could, bust out at any time. If you know how many values you're adding up, you know what your n value is, then instead of doing a whole bunch of work, the answer is simply n times n plus 1 over 2. And we have the same thing for I squared. This would be, what I did here, but if you were doing this a bunch of times, you would have n times n plus 1 times 2n plus 1 over 6. So notice we did that with n being 5 up at the top of the slide, and notice that if we put 5 into here, we'd have 5 times 6 times 11 divided by 6. And you can see that that would in fact be 55, which is what we got over here. So it's a way to do it without having to add everything up together. These are formulas that have been proved. And again, induction's a very common way to do these. There's also one for I to the third. So I'm just going to mention these three because I'm going to use them, 3, 4, and 5. I'm going to use these in some examples. So when you see something like this, express the following in closed form, it's saying take this thing that is in terms of I and basically write it in terms of n. And so the way to think about it is n that you see here is just a constant. It does not change. It's just whatever n is, that is what n is. So if you're going up to 100, your n is 100. So because of that, we can pull that out and then have the sum of I equaling 1 of 2i plus 1 up to n. Now we can't move anything, well, there isn't a huge reason to move anything else out at the moment because 2i is dependent on I and I is changing. So we can't take it out of the summation sign. But the next step that I could do would be now to think about, we know what the summation of I is, that's number 3, and we know what the summation of 1 is, or really any constant, n or c times n, and so we can rewrite this. So that summation for 2i is going to be 2 times the summation of I, which we know is just n times n plus 1 over 2, plus, and then what we would get if we added up a bunch of 1s, which is n. So notice I no longer have summation, I no longer have I, because all I'm doing now is writing everything in terms of n, and now I'm just going to simplify. So really you have 1 over n. This is gone, so you have n squared plus n, and that's n squared plus 2n, but you're multiplying that by 1 over n, so n plus 2. So the point is there that if you wanted to add something like this, you don't need to change your i's a bunch of times. This is the formula for that. This is the closed form. You could just put your n and add 2. So, and notice, I mean, that makes kind of sense. See, you're dividing by a value. So, you know, maybe at the bottom here, hopefully I have space. I'll just show a quick example at the bottom. If we have the sum of I equaling 1, for example, to 5 of 2i plus 1 over 5, notice the 5 I have in my denominator is the same here because in this general form, this is the same value here. So that is required for this problem. And if we were, so we kind of already know the answer should be 5 plus 2 because of what we did earlier. Should be 7. But let's take a look doing it the long version so you can see that they're the same. So we have 1/5 and then the sum I equals 1 to 5 of 2i plus 1. And that's going to be, I'm actually going to write it out here. If I change the 1s and do it 5 times, so if I put in 1 for 2i plus 1, I get 3. If I put in I equals 2, that's going to give me 5. If I put in I equals 3, I get 7. I equals 4 gives me 9, and I equals 5 gives me 11. And that's going to be 1/5 times, and then I add these values together, so I get 15, I get 24, I get 35, not surprisingly, and that answer is 7. So the point is, that's the same as just doing n plus 2. N plus 2 is 5 plus 2, and there we go. So then we have our answer in the same way. So just notice those are equivalent. Okay, so here's one that is a little bit harder. And the big thing is, notice it uses a limit. So it has the idea of a limit here, and that's a big deal for sure. I notice it, you notice it. And so what we're going to do is we're going to first start with the first part, which is just what we just did, and then we'll take the limit at the end. So here we go. So I'm not going to lose my limit, but I'm going to like not think about it for right now. So just like we did before, we can pull this 2 over n out because it's not dependent on the I. And then I have I equals 1 up to n. And I have 1 plus 2i over n, and this is squared. So what I will actually do, like it or not, is I will multiply out what I have inside the summation. So 2 over n, and so I'm just rewriting everything here, nothing new. All right, so I'm going to multiply this out. I'm going to square this. So I get 1 plus 2i over n plus 2i over n is going to be 4i over n. And then I'm going to take and I'm going to square 2i over n. So that's going to give me 4i squared over n squared. So that's what I have now in my summation just by doing all the squaring. Okay, now the reason for doing all this is because we do want to eventually replace those i's. That's the idea. And we're using the properties that we have from the last page. So I have the limit as n approaches infinity, and I have 2 over n, and then I have my summation, I equals 1 to n. And actually, you know what? Even in my notes, I just go right from here where I stop using the summation notation and actually use the properties. So I'll just do that. So what we've learned already from talking about these is that when we sum 1, we get n. So now I'm actually doing the summation of each piece. So this piece, and then this piece, and then this piece, plus, and then the summation of I. So I have 4i over n. So I have 4 over n times the summation of I, and that is the n times n plus 1 over 2. And then we're going to add the next summation, which is the I squared. So 4, and then I've got n squared, and then the I squared. And the I squared is, I've got it, here we go, n times n plus 1 times n, times 2 n plus 1, like that. And that is all over 6. So I'm going to write it like that. Whew. Okay, so I have all of that. Now, the next thing I need to do is really just kind of simplify and think about my limits. So I'm almost there. So we have 2 over n. We have n plus, so notice that I've got like this 4 simplifies with this 2. This n simplifies with this n here. And so that gives us 2 times n plus 1 plus, and then nothing too exciting simplifies there. So I have 2 n plus 1, 2n plus 1, and then over 3n squared. So that's just simplifying the 4 and the 6, but nothing exciting. Okay, so now what I want to show is what would happen if we distribute in that 2 over n, because we're about to take a limit. So if I distribute in the 2 over n, I have 2 over n. I'd have 2 over n, and I'd have 2 over n. So that's what would happen if I distributed. So that's gone now. And the point is to see that this brings up stuff that we talked about in section 3.4 when we talked about limits to infinity, because that's what we're really taking here is a limit to infinity as n goes to infinity. So you end up with having 2 plus, and then you have 4 n plus 1 over n, and then 4 times n plus 1 times 2n plus 1 all over 3n cubed. Okay, and so now I'm ready to take my limit, and what I want you to see is that you're taking the limit of n plus 1 over n, and that's like what we did in section 3.4. Those have the same degree, and so because of that, the limit as n goes to infinity is just going to be the ratio of their coefficients. One of them, because you basically have 4n plus 4, one of them will be 4, and the denominator will just be a coefficient of 1. So the limit as n goes to infinity of 2 is just 2. That's my first piece. The limit here is just 4. And the limit here is, and again, what I want you to see is you really just have to think about what if I were to multiply this out, I'm not going to require you to multiply the whole thing out, but if you were to multiply it out, okay, you're going to get 4n times n times 2n. That's going to be your leading term. 4n times n times 2n. There's going to be a bunch of terms, but the one that you care about is that you're going to have an 8n cubed as your leading term, and then the denominator is a 3n cubed. And so again, when you think about that limit as n goes to infinity, they have the same degree. So this is going to be 8/3, and that's that limit. And then you can add them all together and get, 26/3, or 8 2/3. And so we're going to be doing things in a lot more straightforward way, but this is the way to think about it in terms of a limit. And what I want you to see is that even though n is going to infinity, we got a whole number. Like, our answer is a whole number, and that's a really big deal because n could be anything. N's going to infinity, and yet we're able to add up all these values and still get something that is done. So the last little bit of this is looking at something similar, but kind of putting it all together. So we have the idea of what's called a sampling point. This is just an x value along the x-axis that we're choosing to use for some sort of sum in terms of these rectangles. So we've already talked about how the area is some summation of a bunch of rectangles. And when we talk about left-hand endpoints, right-hand endpoints, so left-hand sum, right-hand sum, we're using specific sampling points, which are, some equal distance. But the point of writing it like this is just saying that they really could be anything. You could choose anything. It's just not as systematic as something like equal subdivisions. So the change in x, as we already talked about, is b minus a over n. So we already talked about that. And so the idea here is that your sampling points are all just coming from taking the side of your endpoint, or the side of your interval, which is a, and then adding on some change in x. But because we want each one, we're going to put the I here, so that as I changes, the number of changes in x's changes, and so that's what moves you along the x-axis. So your x sub naught is just a. X sub 1, not surprisingly, is a plus the change in x. If we did another one, then we'd want 2 change in x's for the next value. And this really does follow what we just did earlier, but it's just that general form. So x sub 3 is a plus 3 times change in x, and so on and so forth. Okay, so let's use this in an example. Find the area under the graph of y equals x squared plus 1 between 0 and 2. So we already looked at this for just x squared. Now we're just rising it up above, and we're going to use this idea of the limit notation in the rectangles in order to get that exact answer, which is not going to be an approximation. So notice you can really kind of think about this. What's really important is kind of thinking about the fact that here you have 1 unit squared, here you have 1 unit squared because length and width are both 1. You have another unit squared here, so you'd say, okay, that's about 3. And then maybe this and this would be 4. And then you've got maybe like 4.5 or so with this up here. So don't forget that really all we're doing is just estimating how much area there is under the curve. And so, you still have the ability to kind of think about it just in terms of rectangles and estimations, in order to check your answer is right. So, oops. Okay. So the way that we look at this is the area that we're trying to find here. Hopefully I can keep my spacing small, right? Small, everyone. The limit as n goes to infinity of the right-hand side is equal to the limit as n goes to infinity of adding up a bunch of these rectangles. So I equals 1 to n and f of x sub I times the change in x. Okay, so, and again, I could have done the left-hand side or the right-hand side because as n goes to infinity, they're the same. Now, if you think about this, the change in x is b minus a. So 2 minus 0 over n, or 2 over n. Okay. Now, your sampling points, so that's, I mean, what that's telling you is that, you know, so your first value, x sub 0, would just be 0. But I'm using the right-hand sum, so I'm going to start with x sub 1. So x sub 1 is 2 over n. And then my x sub 2 is just adding another change in x, another delta x. So 2 over n plus 2 over n is 4 over n. And x sub 3 would be adding another 2 over n, so 6 over n. So it's just telling us where we would sit along the x-axis along here, depending, but again, it just changes depending on how many rectangles you're doing. So the big idea would be that x sub I is this 0 plus I times this, you know, change in x. So just however many we have, that's, you know, going to tell us. So yeah, so that's it. So x sub I is, I shouldn't say that's it, 2i over n. Okay, now over here on the other side, I'm going to say that because of what I wrote here, that tells me that the limit as n goes to infinity, so what I'm doing is I'm going to add up an infinite number of these rectangles. I have I equals 1 to n. Now f of x sub I is just take my x sub I, 2i over n, and then square it. Because, I mean, that's what it is. That's what x is. That's right here. And then I add 1. And then I multiply that by the change in x, which is right here. Change in x, we already said was, okay. Now, what this is now this is almost exactly like what we've already seen in the problem above. So if you want, you could pause it and you could see, could you write this out and then make some changes in terms of the i's that you might have, and then take your limit and see what you get. Your answer should end up being, you know, a number that is done, is a finite number. So I could write limit as n goes to infinity. I'm going to take out my 2 over n because it's not dependent on I. And, ooh, okay, sorry, my summation is ugly, ugly, ugly. Okay, so so what I have left here is I equals 1 to n, and then notice I have 4i squared over n squared, and then plus 1. That's what I have there, because I'm just squaring just that piece. And so now I'm going to come down here, the limit as n goes to infinity. So I have 2 over n, and then now I can think about what's going to happen when I change these to the, you know, what we know. So I have 4, and then our I squared, which we already talked about, which I just don't have memorized, but is n times n plus 1 times 2n plus 1, like that. There we go. All over 6. Perfect. And then we have, don't forget my n squared down here. I got to include that, so I got my n squared there, and then plus adding up the summation of 1, so that's just n. Got it. Okay, so now when we multiply this out, limit as n goes to infinity, we're going to have, okay, so the way I'm going to write this is, I want you to notice that I'll have 4 times n plus 1 times 2n plus 1 over 3n squared. So my n here simplifies with my n here, and this 2 I'm going to simplify with this 6. So that's how come I get what you see here. And then when I do that distributive property with my n over here, this is going to be just plus 2. And then what you can see is that, and I'll show you, if we were to multiply out our numerator now, we'd have 8n squared plus 12n plus 4, and that's divided by a 3n squared. And then we have our plus 2. So the key thing to see is, again, from section 3.4, we see that these are just polynomials here. And because they have the same degree, as n goes to infinity, we're going to have 8 over 3 plus 2. And that's going to give us, 14 over 3. And that's units squared. That's also 4 2/3. So remember when I was talking about the estimation over here, it's completely within the realm of possibility that our answer is right, because we can just see from looking underneath the curve that we had about four rectangles and something. So getting, 4 2/3 makes a lot of sense. So that's our answer. It's a lot of work, but that is the way to find the area under the curve using the idea of the Riemann sums. So let's talk about the last one. It's a lot shorter, I promise. It wants us to think about what we would be kind of the function and the interval that we'd be talking about that would create something like this. So the way that we would look at a problem like this is we'd really just notice that you have this piece and that is squared, to the fifth. And the problem that we did, notice what it looked like when we did that problem earlier. So we had that kind of interesting thing squared plus 1. So we should see that this would be the function x to the fifth. And x sub I, the sampling points, remember are a plus I times delta x. Okay. And that is what goes inside the function. So that's this piece right here, 3 plus 4i over n. So really just from that, we learn that a is 3 and delta x is 4 over n. And then from there, that really tells us that since delta x is b minus a over n, and we know that that is 4 over n, we know that b minus a is 4, but we know that a is 3. So b minus 3 equals 4, and that tells us that b equals 7. So what we've learned is that, and I'll put it here, the region is, because it says determine a region, the region is this function from 3 to 7. And that's section 4.1.